Hello, this is Mr. Hebner back at home. We're doing part 2 of the balancing half reactions, redox reactions, and this is method 2. The video got cut off due to lack of space, but we got plenty of space now. Alright, so recapping. First, you got to find the oxidation states of each element. And once you do that, you got to determine what's oxidized and what's reduced. So we got Mn, looks like it's being reduced, and carbon looks like it's being oxidized, losing electrons, where manganese was gaining electrons. So divide equations into two half reactions is the next thing. We have our oxidation of our carbon, and we have our reduction of our manganese. We have to make sure we show how many electrons are being transferred. We've got +3 to +4. It's 1 electron being released. Here we've got +7 to +2. That's 5 electrons that are being gained. Once we have that, you have to balance elements other than H and O. So in this case, that would include Mn in carbon. So Mn is balanced, 1 on each side. But carbon, there are 2, and here there's 1. So I'm going to have to add a 2 coefficient to balance that out. Now if we look at that, we now have 2 carbons that are +3 going to +4. So that's a total of 2 electrons being transferred. Alright, so now we go to step 2. Next, balance oxygen atoms by adding H2O as needed. So here we got oxygen is +4, or there's 4 of them, and here there's 2 times 2, 4 oxygen. So it's fine over there. Here we got 4 oxygens, here we have 0. So on this side, that's where I'm going to have to add my H2O. And since I have 4 of them here, looks like I'm going to have to add a 4 right in front of the H2O. 4 oxygens, but now I have 4 times 2 is 8 hydrogens. That's where number 3, step 3, then balance H atoms by adding H plus as needed. Alright, so I'm going to put H plus on this side, and 4 times 2 is 8. I'm going to need 8 of them. That's the hydrogen ions from the acid in the acidic solution. Alright, and this method, to recap, is for when you do not have the specter ions present for solutions that occur in acidic solutions. Alright, it says finally balance the charge by adding electrons as needed. Okay, here I got 5 and here I got 2. So I'm going to find the lowest common denominator, which is 10. So what times 2 equals 10? 5. So I'm going to multiply my oxidation by 5. And what times 5 equals 10? That's 2. I'm going to multiply my reduction by 2. So I'm going to rewrite this. 5 times 1 is 5. So 5 C2O4. 5 C2O4 aqueous, and then I've got 5, too bad it can't be, here we go, 5 times 2 is 10, 5 times 2 is 10, so I got 10 CO2 plus 10 electrons. Alright, and then we've got reduction. 2 times 8 is 16. 2 times 5 is 10. Right, so I got 16 H plus 10 electrons. And then we've got 2 times 1 MnO4. 2 MnO4. And then that brings us to 2 times Mn. 2 times 4H2O is 8. So 2 Mn. And this is 8 H2O. Okay. All right. It says add the two half reactions and simplify wherever species appear on both sides. All right, so the last step is combining these half reactions. We have 16H plus 2MnO4 plus 5 C2O4 plus 10 electrons. Just so I have enough room, this produces 10 CO2 plus 2 Mn plus 2 plus 8 H2O plus 10 electrons. Alright, now the last step, check the number of atoms balances on the reactant and product side. Check to make sure the total number of charge on the left is the same as the total charge on the right. So we've got 16 H's, 8 times 2 is 16, 2 Mn's, 2 times 4 is 8, plus 20 is 28, 5 times 4 is 20. That gives us 10 times 2 is 20, plus 8 is 28, 10 electrons, and it looks like that's about it. 5 times 2 is 10, 10, and it is absolutely balanced. Alright, moving on to the last part. You may be familiar with this in your sophomore level chemistry class. Looking at reactivity of elements, kind of single replacement reactions might ring a bell. So what we're talking right here, we got, oh, it says single replacement reactions right there. Electrons are transferred between a free element and a monatomic ion. So here's a monatomic ion, copper, and here's a free element. And the one that oxidizes more or more readily loses electrons, that's what's going to end up in the compound. So what you need to do is be familiar with the activity series. Let's see if I can find it. Okay, let me pause this while I find it. Alright, here it is. The activity series looks like lithium is the most readily oxidized or the best reducing agent. And as we go down, they become less and less oxidized. So we're looking at iron versus copper. Iron is definitely more oxidized. Therefore, it will replace the other ion. So in this case, since iron's higher up on the activity series, it's more readily oxidized. It's going to boot copper out, and sulfate's going to steal its electrons because iron wants its electrons to be taken, wants to be oxidized. So that's going to form copper metal plus iron sulfate, so that is a true reaction. Alright, moving down here, it says a more active metal always replaces the ion of a less active metal. That's what that happened. And it also occurs with nonmetals. That's what the next second bullet is saying. So here we go, nonmetals. Fluorine is the most readily oxidized, and sulfur being the least in that activity series. And those are the elements they commonly see, especially the halogens. Fluorine, chlorine, bromine, iodine. Fluorine being higher up on the periodic table. Alright, examples. Use reactivity series to predict whether reactions will occur between the following reactants. Write equations where relevant. Alright, so this would be the time where you try them out, but we'll do this first one. We're looking at silver versus the other metal, copper. I know jewelry elements are typically not wanting to oxidize, although silver does tarnish, unfortunately. but gold, it's going to be really hard for it to tarnish. Even copper, which is why it's used in piping, water pipes. Alright, silver versus copper. We got copper down there and silver even further. So copper is going to be more readily oxidized. Therefore, nothing's going to happen. So copper is going to, its electrons are going to be taken by chlorine. So no reaction. How about iron versus aluminum? Well, let's look at that activity series. Iron's up here. Aluminum's up there. So aluminum is going to be more readily oxidized, therefore ending in the compound aluminum. Yep, this reaction occurs. So here we go. We're going to have iron by itself plus Al NO3, and I know that nitrate's -1 and aluminum's 3+. You can always look at the periodic table to double check. You crisscross it. You got 3 nitrates. Ooh, so least common factor between 2 and 3 is 6. So we're going to need 3 and 2. That gets us 6 nitrates. But now we need 2 aluminums, 3 irons, 3 irons, and it's balanced. So I would pause the video right now and try to do letter C and D, and then I'll walk you through them. Alright, welcome back. Hope you had a great little break. We're looking at bromine, a nonmetal, with, well, we're not comparing it with sodium, we're comparing it with the other nonmetal, iodine. So we gotta look at which one is more reactive or more readily oxidized. Is it bromine or is it iodine? Here's bromine. Okay, iodine is higher up than bromine, so bromine is more readily oxidized and therefore more easily reactive. That's bromine. So bromine will end up in the compound, so this reaction will in fact occur. Two iodines, 1 iodine, 2 iodines, 2 sodiums, 2 sodiums, 2 bromines, 2 bromines, and it's balanced. Alright, next, Kcl Plus I2. Again, we only got 1 cation. The other 2 are anions, so those are going to do the flip-flopping, potentially, if iodine is more reactive. So just double checking. Iodine's down here and chlorine is up here. Chlorine is more readily oxidized, therefore more reactive. So chlorine will end up in the compound, and it looks like chlorine already is in the compound, so this is a no reaction. And that concludes the notes. Hopefully you enjoyed. I will see you later.